Somewhere in southern Siberia, the ground never stopped pulling apart, not with an earthquake, not in a single violent moment. Slowly, patiently, year after year, for millions of years, the Earth's crust continued to open, leaving behind something that should not exist. Today it is called Lake Baikal. It is not the largest lake on Earth. It ranks only seventh by surface area, and yet it holds one-fifth of all the unfrozen freshwater on the planet's surface. Not because it is wide, because it is impossibly deep. The water falls 5,387 feet straight down, deeper than 9 Empire State Buildings stacked one above another, and even then, you have not reached the bottom of the crack that created it. Most lakes disappear after roughly 20,000 years. Baikal has survived for 25 million. It has watched mountain ranges rise, climates collapse, and entire geological ages come and go while continuing to grow deeper. What that span of time created exists almost nowhere else on Earth. Nearly 80% of the animals living here exist nowhere else, not in another lake, not in another river, not anywhere. There is a fish so delicate that direct sunlight begins to destroy it. There is a seal living hundreds of miles from the nearest ocean, with no complete explanation for how its ancestors ever arrived. And deep below the surface, where no lake was ever expected to behave this way, superheated water rises from hydrothermal vents, once thought to belong only to the ocean. When scientists finally reached the deepest known part of Lake Baikal in 2008, using the same submersibles that had explored the wreck of the Titanic, they discovered the lake was deeper than anyone had calculated. Even today, much of its floor remains unexplored. Much of what lives there has never been named. Tonight, we're descending into the deepest freshwater lake on Earth to uncover why it exists, what survives in its darkness, and why this ancient body of water has been rewriting freshwater science for millions of years. Before we continue, if there's a documentary topic you'd enjoy seeing us explore in the future, leave it in the comments. I always enjoy reading your suggestions. Let's descend beneath the surface of the oldest lake on Earth. Every landscape carries a memory of the forces that shaped it. In southern Siberia, that memory is written into stone that has never stopped shifting, almost too gradually for a human lifetime to notice. The shoreline appears steady, forests stand rooted along the mountains, and the water rests within familiar boundaries. Far below, however, the continent remains in motion, continuing a process that began around 25 million years ago and has never reached its conclusion. The foundation of Lake Baikal lies within the Baikal Rift Zone, a fracture running through the continental crust where the Siberian platform and the Amurian plate continue drawing apart. Their movement measures less than an inch each year, yet time transforms even the smallest motion into extraordinary change. The same tectonic process that once opened the Atlantic Ocean is unfolding here across dry land, following a rhythm so gradual that generations pass before its progress becomes visible. As tension spread through the crust, great blocks of rock fractured and settled downward. Instead of producing a broad basin with gently sloping sides, the land formed a long, narrow trench enclosed by steep walls. Today, that trench stretches for nearly 247 miles, while reaching almost 31 miles across at its widest point. Its shape bears little resemblance to lakes carved by glaciers. It resembles a continental scar whose walls descend almost directly toward remarkable depths. Water steadily gathered inside this expanding depression. More than 330 rivers and streams carried snowmelt, rainwater, dissolved minerals, and fragments of distant mountains into the growing basin. Only a single river, The Angara River carries water away. Every season adds another small contribution, each current delivering another layer to a system that has accumulated freshwater across spans of time almost impossible to picture. Ordinary lakes rarely endure for very long in geological terms. Soil, sand, fallen plants, and drifting sediments gradually settle across their floors until shallow marshes replace open water. The cycle eventually ends with forest or grassland where water once stood. Lake Baikal follows another path entirely because the floor beneath it continues descending. Even as sediment settles through the water, the rift keeps creating additional space below. The basin deepens more rapidly than nature can fill it, preserving the lake across ages that erased countless others. Those accumulated sediments now form an archive extending more than 4 miles beneath the present lake floor. Layer upon layer has compressed beneath immense weight, preserving traces of ancient forests, volcanic ash, pollen carried by distant winds, microscopic organisms, and chemical signatures from climates separated by millions of years. Each layer became another page without disturbing those already resting below, creating one of Earth's longest uninterrupted environmental records. Everything that makes Lake Baikal extraordinary begins with this enduring fracture. Its immense depth shapes water pressure unlike any other freshwater lake. Isolation separated its inhabitants from surrounding rivers for millions of years, allowing life to follow paths found nowhere else. Darkness reached farther downward than expected for inland waters, while geological motion maintained the stage upon which every later adaptation unfolded. The living world of Baikal exists because the continent beneath it never finished pulling itself apart. A lake can be measured by its shoreline, its depth, or the volume of water it holds. Lake Baikal invites another measure altogether, the character of the water itself. Every drop carries properties that seem better suited to theory than reality, preserving conditions that freshwater scientists once believed could not persist through such extraordinary depth. For in most deep lakes, the water gradually separates into distinct layers. Sunlight warms the upper surface, leaving lighter water above, while colder, denser water settles farther down. Oxygen supplied by the atmosphere remains concentrated near the top, while the deepest reaches slowly lose the supply required for animals with complex bodies. Many lake bottoms become places where oxygen grows scarce, limiting life to hardy microorganisms adapted to those conditions. Lake Baikal follows another pattern. Even at a depth of 5,387 feet, dissolved oxygen remains between roughly 3/4 and 4/5 of the concentration measured near the surface. Fish, crustaceans, and countless other organisms continue living throughout the full depth of the basin because fresh oxygen reaches places that should have been isolated from the atmosphere long ago. The explanation arrives each winter when the surface cools until it approaches the freezing point. At that moment, the upper water becomes denser than the layers below and begins to descend. That sinking water carries dissolved oxygen with it, while deeper water rises to replace it. The circulation spreads through the entire lake, renewing the water column from top to bottom in a yearly cycle that has repeated across millions of winters. Chemically, the lake is equally unusual. Scientists classify it as ultra oligotrophic, meaning it contains extremely low concentrations of nutrients, suspended particles, and dissolved minerals. Rivers entering the basin certainly carry material from surrounding landscapes, yet the lake remains astonishingly clear because very little remains drifting through the water for long. During winter, visibility can extend 130 feet beneath the ice, revealing distances comparable to looking down the height of a 13-story building through glass. This remarkable clarity depends upon one creature so small that it escapes ordinary notice. Epischura baicalensis is a tiny crustacean, almost transparent, scarcely larger than a grain of rice. Though nearly invisible to the human eye, it dominates the lake more completely than almost any comparable organism dominates another freshwater ecosystem. Around 96% of all zooplankton biomass belongs to this single species. Every day, these minute animals consume algae, bacteria, and drifting organic particles suspended in the water. Their feeding never truly pauses. Across the immense population inhabiting Lake Baikal, the combined filtration becomes almost beyond imagination. Limnologist Georgi Galazi estimated that they process between 500 and 1,000 cubic miles of water each year, many times greater than the total annual inflow arriving from every river and stream feeding the lake. The consequence reaches every corner of the basin. Countless generations of these crustaceans have strained microscopic debris from the water again and again, allowing exceptional transparency to endure, while helping preserve the stable chemistry upon which the entire ecosystem depends. Episkura itself survives only where water remains cold, rich in oxygen, and chemically balanced. Its existence has become woven into the identity of the lake, each tiny body participating in a cycle that has shaped the freshwater world of Baikal for millions of years. Far from the shoreline, where daylight loses its strength and pressure steadily increases, one fish occupies almost every layer of the lake. It is rarely seen by human eyes in its natural world, yet by total weight it is the dominant fish of Lake Baikal. This strange resident has no close equivalent in any other freshwater ecosystem, and nearly every feature of its body reflects millions of years spent adapting to conditions found nowhere else. Scientists recognize two living species within this remarkable lineage: Chamaephorus baikalensis, the larger form, and Chamaephorus debowskii, the smaller. Both exist only within Lake Baikal, forming the world's only family of deep freshwater fish. Together, they account for roughly 150,000 tons of living biomass, close to 70% of all fish weight in the lake. They accomplish this without gathering into schools, without supporting commercial fisheries, and without drawing much attention from the surface above. Their appearance seems almost unfinished. The skin lacks scales and carries a faint pink glow, while muscles remain nearly transparent. Internal organs can be seen through the body wall, giving the fish an appearance unlike ordinary freshwater species. Early Russian naturalists described living specimens as creatures whose bones appeared visible from the outside, an observation that still captures the unusual delicacy of their form. Almost 40% of the body consists of oily fat rich in vitamin A. That reserve provides much more than stored energy. It gives the fish natural buoyancy, allowing it to remain suspended through the water column without relying upon a swim bladder. Most fish adjust their position by controlling gases inside specialized organs. The Golomyanka accomplishes the same task through its remarkable chemistry, drifting with precision across an enormous range of depths while avoiding the physical limitations that affect many other fishes. This adaptation grants access to nearly the entire lake. Individuals have been recorded from surface waters to almost 5,000 feet below, making them the most depth-tolerant freshwater fish known. Few animals experience such dramatic changes in pressure during ordinary life, yet the Golomyanka moves through them with apparent ease, occupying regions that would challenge almost every other freshwater vertebrate. Each evening begins another steady ascent. As tiny crustaceans drift upward through the water, the fish follows the movement, feeding where food becomes more abundant. Morning brings the reverse journey, carrying it back toward colder depths. The complete round trip approaches a mile every day. Vision contributes little during these travels. Instead, the fish depends largely upon its lateral line, a pressure sensing organ running along each side of the body that detects subtle water movement created by nearby objects and living creatures. Its body remains perfectly suited to darkness and cold, yet those same adaptations become fragile at the surface. Exposure to direct sunlight causes the oily tissues to break down with surprising speed. The body collapses until little remains beyond oil and delicate bones. Along Baikal's shores, people once gathered carcasses washed ashore after storms, rendering the oil into lamp fuel and traditional remedies for aching joints. Even in death, this transparent fish continued serving the communities living beside the lake, carrying within its unusual body another chapter in Baikal's long natural history. Life in Lake Baikal often follows rules that seem to belong somewhere else. Even after the Golomyanka's transparent body and extraordinary migrations are understood, another layer of its existence appears, one that reshapes the entire rhythm of its life. Reproduction. The event that ensures another generation carries a cost so immense that it frequently becomes the final act of the mother's life. Most fish release eggs into the water, leaving currents and chance to determine what follows. The Golomyanka follows a different path. It is viviparous, developing its offspring within the mother's body before releasing fully living larvae into the surrounding water. Among freshwater fish occupying such cold depths, this strategy is exceptionally uncommon. The developing young remain protected until the moment they enter the lake, already capable of drifting into the enormous water column that surrounds them. A single female can produce as many as 3,000 living larvae during one birth. The number is astonishing when considered alongside the fish's delicate frame. Nearly every reserve of energy gathered throughout its life becomes invested in that single event. Instead of spreading reproduction across repeated spawning seasons, the Golomyanka often concentrates almost everything into one overwhelming effort. For many females, that effort cannot be survived. The physical demands of producing thousands of living young exhaust the body's remaining resources. Soon afterward, the mother dies, leaving behind only the next generation suspended within the cold water. A smaller number recover sufficiently to reproduce once more, while only the rarest individuals survive long enough for a third birth. Even under favorable conditions, the species seldom lives beyond 6 years, a surprisingly brief lifespan for a fish inhabiting water where low temperatures usually slow metabolism and extend longevity. Survival becomes even more uncertain after birth because danger arrives from an unexpected direction. Adult Golomyanka feed upon many drifting organisms, yet documented observations reveal another item within their diet. They consume their own species, including larvae and young juveniles. Cannibalism forms a regular part of their ecology, reducing competition while providing nourishment from the very offspring that escaped only moments earlier into the open lake. Death never interrupts the larger cycle unfolding through Baikal. When a Golomyanka dies from childbirth, old age, or another predator, its body begins descending through the water. Rich stores of oily fat remain locked inside its tissues, carrying valuable energy toward creatures waiting at many different depths. Very little organic material goes unused inside this ecosystem. Each sinking body becomes another transfer of nourishment through a community shaped by long isolation. Among the animals benefiting most from this remarkable fish is one that seems even less likely to inhabit a freshwater lake. The Nerpa, also known as the Baikal seal, relies heavily upon Golomyanka as its principal source of food. The fish's abundant fat provides concentrated calories, allowing a warm-blooded mammal to maintain body temperature throughout a lake that remains close to freezing for much of the year. Predator and prey have become so closely linked that the fortunes of one are woven tightly into the survival of the other. Within this relationship, the Golomyanka supports life twice. It fills the lake with thousands of living young, and after its own life ends, its body continues nourishing another remarkable resident. Every generation becomes part of an uninterrupted exchange of energy that has continued across countless ages, preserving one of the most distinctive food webs found in any freshwater environment on Earth. Among all the creatures carried by Lake Baikal's long history, one seems especially difficult to place. A seal belongs to drifting sea ice, rolling surf, and coastlines shaped by tides. It does not belong in a freshwater lake surrounded by mountains and forests, separated from every ocean by hundreds of miles of land. Even so, the Nerpa has spent countless generations living exactly there, as though the lake had always been its natural home. Known scientifically as Pusa siberica, the Nerpa completes every stage of its life in freshwater. It is born there, hunts there, raises its young there, and eventually dies there without ever entering salt water. No other seal species follows this pattern. The lake supports a thriving population of roughly 100,000 individuals, large enough to remain stable without outside assistance. This is not an isolated remnant nearing extinction. It is a healthy population that has become fully established within one of the most unusual habitats occupied by any marine mammal's descendant. Geography only deepens the mystery. The nearest Arctic coastline lies hundreds of miles away, separated from Lake Baikal by rivers that no longer provide a direct aquatic route. A modern seal leaving the lake would find no continuous path leading back to the sea. Every surrounding landscape seems to insist that such an animal should never have reached this place in the first place. Genetics, however, preserve a memory that geography alone cannot explain. The Nerpa's closest living relative is the ringed seal of the Arctic, a species that depends upon salt water throughout its life. Their close relationship points toward a shared ancestor that once inhabited northern seas. At some point in the distant past, members of that marine lineage entered the interior of Siberia and established a population inside what would become Lake Baikal. The leading explanation reaches back to the Pleistocene epoch, the long interval marked by repeated ice ages. During that period, glaciers, melting water, and changing sea levels repeatedly reshaped the drainage systems of northern Asia. Rivers that are disconnected today likely formed temporary pathways linking distant basins. Many researchers suggest that ancestral ringed seals gradually traveled through one of these freshwater corridors, possibly along an early form of the Yenisei and Angara river system, following expanding waterways farther inland until they reached Baikal. The landscape never remained fixed. As glaciers retreated and river systems shifted, those temporary connections disappeared. Waterways changed direction, valleys separated, and the route back toward the Arctic vanished. A population of seals remained enclosed within Lake Baikal, isolated from its marine relatives by geography that continued evolving around it. No complete fossil record traces each stage of this remarkable journey. The evidence comes instead from genetic relationships, geological reconstruction, and the history of ancient drainage networks. Together, they form a convincing hypothesis, though many details remain beyond direct observation. The path itself has faded from the landscape, leaving only clues preserved in rocks and inherited characteristics. The Nerpa therefore represents more than an unusual freshwater mammal. It stands as an example of a species that adapted so completely to a transformed environment that almost every visible reminder of its marine ancestry disappeared. Its body still carries the inheritance of distant northern seas, while its daily life belongs entirely to Baikal. The route that brought it here has almost dissolved into Earth's history, yet the animal itself continues swimming through the lake as living evidence that landscapes change, rivers wander, and evolution preserves stories long after the roads themselves have vanished. Evolution often begins with inheritance, yet over enough generations, inheritance becomes transformed into something entirely new. The Nerpa still carries the outline of its Arctic ancestry, but every important detail has been reshaped by the demands of Lake Baikal. Time, cold water, and isolation gradually refined an animal that no longer fits comfortably alongside any other seal living on Earth. A Nerpa can descend to depths approaching 1,300 feet and remain underwater for as long as 70 minutes before returning to breathe. Even among seals, those abilities stand apart. Many marine relatives surface after only 20 or 30 minutes, balancing their dives against the limited oxygen carried within their bodies. The Nerpa extends that limit through a collection of physical adaptations working together with remarkable efficiency. One of the most important changes cannot be seen from the outside. Relative to its size, the Nerpa carries an unusually large volume of blood. Every heartbeat delivers oxygen that had been gathered during a single breath at the surface, creating a reserve far greater than expected for a mammal of comparable weight. That expanded internal supply delays the moment when another breath becomes necessary, allowing long descents through Baikal's immense water column. Its muscles provide another solution. They contain exceptional concentrations of myoglobin, the oxygen-storing protein responsible for the deep color found in dark meat. Rather than relying entirely upon oxygen circulating through the bloodstream, working muscles draw from these stored reserves while submerged. Even after the lungs have emptied, movement continues with remarkable efficiency, allowing the seal to pursue prey through prolonged dives where many other mammals would already be returning toward the surface. The clarity of Baikal's water also shaped the Nerpa's senses. During winter, visibility can extend nearly 130 feet through the lake. Light penetrates deeply enough that hunting by vision remains practical across distances impossible in most freshwater environments. Large, forward-facing eyes gather the available light, helping the seal locate moving fish within water that often rivals the clarity of carefully maintained swimming pools. Winter introduces another challenge, unlike anything experienced during warmer months. Ice eventually seals the lake from shore to shore, removing open access to the air above. The Nerpa responds with behavior inherited from distant Arctic ancestors but adapted perfectly to freshwater conditions. Using strong claws on its forelimbs, it scratches breathing holes through the ice from below, returning to them repeatedly throughout the frozen season. Several openings may be maintained across an individual's territory, forming a dependable network connecting water and air. Spring brings the arrival of newborn pups. They enter the world upon the ice, wrapped in soft white fur that blends naturally with snow covering the frozen surface. This coloration evolved long before the Nerpa became isolated within Baikal, yet it continues serving the young effectively. It remains one of many inherited characteristics preserved across countless generations despite the dramatic change in habitat. Throughout every season, the Golomyanka remains central to the seal's survival. Rich deposits of oily fat within that unusual fish provide concentrated energy, supporting the demanding metabolism required by a warm-blooded mammal living in water that stays close to freezing for much of the year. Every successful hunt strengthens a partnership shaped through shared evolution inside the same lake. Seen from a distance, the Nerpa resembles other seals. Looking more closely reveals an animal rewritten by its surroundings. The Arctic supplied its beginnings, while Lake Baikal patiently revised every important chapter that followed, producing a freshwater seal whose physiology belongs entirely to the world that created it. If the deepest parts of Lake Baikal could be surveyed one handful of sediment at a time, another community would gradually reveal itself. It does not announce its presence with large bodies or dramatic movements. Instead, the lake floor is animated by countless small crustaceans moving across rocks, sponge colonies, and layers of organic debris. Together, they shape the foundation upon which much of the deep ecosystem depends. These animals are amphipods, small shrimp-like crustaceans that fill an astonishing variety of roles. Some measure only a few fractions of an inch, while larger species approach several inches in length. Their bodies curve slightly from head to tail, allowing them to crawl, swim, or burrow with equal ease. Within Lake Baikal, they serve as grazers, scavengers, predators, and recyclers, carrying out nearly every ecological task available across the bottom of the basin. Freshwater lakes elsewhere usually contain only a modest assortment of amphipod species. Baikal tells a very different story. Researchers have described around 350 endemic species living within this single lake that represents roughly one-third of every freshwater amphipod species known to science. None of them naturally occur in neighboring rivers, nearby lakes, or any surrounding watershed. Each lineage evolved entirely inside Baikal, shaped by millions of years of separation from the outside world. Their abundance is equally extraordinary. Measured by total weight, amphipods account for roughly 90% of the benthic biomass across the lake floor. Nearly every large concentration of animal life resting upon the sediment belongs to this remarkable group. Wherever organic material settles from above, amphipods are usually present to consume, redistribute, or transform it into resources available for other organisms. No single lifestyle defines them. Certain species browse across living freshwater sponges, feeding without destroying the larger colony. Others specialize in consuming dead plants and animals that drift downward from the water above. Some actively hunt smaller invertebrates, including other amphipods, turning the lake floor into a complex web of predator and prey relationships. Hundreds of closely related species have divided the environment into remarkably specialized occupations, allowing many forms to coexist within the same landscape without competing directly for identical resources. Pressure adds another challenge. At depths approaching 5,000 feet, the weight of the overlying water would damage the tissues of most freshwater animals. Baikal's deepest amphipods have gradually evolved bodies capable of functioning under those extreme conditions. Their adaptations developed independently from those of marine deep-sea crustaceans, making them especially valuable to scientists studying how freshwater life responds to crushing hydrostatic pressure. Similar environmental forces produced comparable solutions, even though the evolutionary histories remained entirely separate. Cold presents an equally demanding obstacle. Water close to 32 degrees Fahrenheit slows ordinary biological processes, yet these crustaceans remain active throughout the year. Their enzymes continue supporting metabolism, while the chemistry of their cell membranes allows normal function at temperatures that would severely impair many other animals. Researchers studying cold adapted biology examine these mechanisms for broader insights into how living cells remain operational under persistent low temperatures. Every movement across the sediment contributes to the larger ecosystem. Amphipods remove decaying material before it accumulates, transfer nutrients through the food web, provide nourishment for fish and other predators, and maintain the living fabric covering Baikal's floor. Their constant activity transforms what might appear to be an empty bottom into one of the most densely inhabited freshwater environments on Earth, preparing the ground for another community that rises directly from the rocks themselves. Life on the floor of Lake Baikal does not spread evenly across bare sediment. In many places, it gathers around living structures that rise from the rocks themselves, creating shelter where little would otherwise exist. At first glance, they resemble underwater shrubs or branching coral, yet they belong to an entirely different group of organisms. These are freshwater sponges, and nowhere else on Earth have they transformed a lake in quite the same way. Freshwater sponges occur on every inhabited continent, although they usually remain modest in size. Most cling to shallow rocks near shorelines, forming thin crusts or small clusters that rarely dominate their surroundings. They depend upon sunlight filtering through clear water and seldom extend into great depths. Their appearance is so ordinary that many visitors pass them without realizing they are looking at living animals. Baikal rewrote those limits long ago. Here, the sponges reach dimensions comparable to those of marine reef species, spreading into thick branching forms that can survive as deep as 3,280 feet. No other freshwater lake supports sponge communities occupying such profound depths. They have expanded into territory where their relatives elsewhere could never persist, becoming one of the defining features of the lake's lower world. Their green color comes from microscopic algae living inside their tissues. This partnership benefits both participants. The algae receive protection and access to dissolved nutrients, while the sponge gains additional energy produced through photosynthesis wherever enough light reaches the water. The relationship has endured for immense spans of time, allowing these colonies to grow into intricate formations that reshape the landscape surrounding them. Those living branches become homes for many other species. Small invertebrates shelter among the sponge network. Fish seek refuge between its openings, and countless animals feed upon organisms growing across its surface. The colonies create physical complexity within an environment that would otherwise consist largely of exposed stone and sediment. Every additional branch increases the number of places where another form of life can settle, feed, or reproduce. Among the beneficiaries is the endangered Baikal sturgeon, one of the lake's oldest surviving fish lineages. It feeds extensively upon mollusks living within and around the sponge beds. The sponges support the mollusks nourish the sturgeon, and another thread is woven into the larger ecological fabric, connecting very different organisms across the lake floor. One stationary animal ultimately helps sustain a fish descended from ancestors that swam through waters long vanished from Earth. Genetic studies have introduced another remarkable possibility. Certain Baikal sponge lineages display molecular patterns suggesting partial ancestry connected to descendants of life once associated with the Tethys Sea, an immense ancient ocean that covered parts of Central Asia before continental collisions raised the Himalayan mountains. The connection remains an area of active scientific investigation, yet it hints that these freshwater sponges may preserve biological echoes reaching back to marine worlds that disappeared tens of millions of years ago. Seen through that perspective, the sponge colonies become more than unusual freshwater organisms. They function as enduring architecture built gradually across geological time, providing stable foundations upon which entire communities depend. Their branches define neighborhoods for the lake floor, supporting life through persistence rather than movement. Long after individual amphipods, fish, or mollusks have completed their brief lives, the sponge colonies continue expanding, patiently shaping the underwater landscape, while another, even more unexpected feature waits farther below, where the lake meets the restless crust of the earth. At the deepest reaches of Lake Baikal, the lake floor is no longer shaped only by biology. Heat from within the earth enters the story, rising through fractures that have remained active since the basin first began opening millions of years ago. These openings release warm, mineral, rich water into an environment where almost everything else remains close to the freezing point. The contrast is gentle by volcanic standards, yet it changes the character of the surrounding landscape in profound ways. Hydrothermal vents form where groundwater seeps downward through cracks in the crust, reaches hot rock deep below, absorbs dissolved minerals, and eventually returns upward through the lake floor. For many years, scientists believed such systems belonged exclusively to the deep ocean, where spreading seafloors and volcanic ridges provided the necessary geological setting. Lake Baikal eventually proved that assumption incomplete. Its position within an active continental rift supplies the same fundamental conditions, even though the surrounding environment is entirely freshwater. The water emerging from these vents differs greatly from the spectacular black smokers found on the ocean floor. Marine vent fluids can exceed 750 degrees Fahrenheit, producing towering mineral chimneys visible from great distances. Baikal's vents operate far more gently. The warmest measured fluids approach about 60 degrees Fahrenheit, entering surrounding water that remains close to 37 degrees Fahrenheit. Even this modest temperature difference creates localized habitats unlike any other part of the lake. No towering chimneys rise from these freshwater vents. Warm mineral-rich water escapes instead through broad seeping zones, spreading gradually across sections of the sediment before mixing into the surrounding lake. The activity often appears subtle, almost blending into the landscape, yet it continuously reshapes nearby chemistry. Minerals dissolved deep within the crust become available to organisms living at the bottom, creating conditions that differ from those only a short distance away. Life gathers wherever these seeps emerge. Sponge colonies establish themselves near the warmer ground. Amphipods patrol the surrounding sediment, leeches occupy sheltered spaces, and dense microbial mats spread across favorable surfaces. The arrangement closely resembles communities surrounding hydrothermal vents in the deep ocean, despite developing independently within freshwater. Similar environmental pressures guided unrelated organisms toward comparable ecological patterns, demonstrating how life repeatedly organizes itself when given similar opportunities. Geological activity contributes something else as well. Methane rises steadily through the sediment from deep underground, carried upward by processes unfolding far below the lake floor. Bubble after bubble escapes through narrow pathways, continuing a release that has persisted over immense spans of geological time. Much of this methane never reaches the surface in its original form. At depths greater than roughly 1,250 feet, pressure and low temperature combine to lock methane inside crystalline structures known as gas hydrates. In these remarkable formations, water molecules arrange themselves into rigid cages surrounding methane molecules, creating solids that resemble ordinary ice while containing large amounts of trapped gas. They remain stable only under the extreme conditions found deep within the lake, breaking apart if pressure falls or temperatures rise sufficiently. These vent fields reveal that Lake Baikal is far more than an exceptionally deep body of fresh water. Geological energy continues flowing upward through its floor, supplying minerals, warmth, methane, and chemical diversity to organisms living far beyond the reach of sunlight. The deepest parts of the basin, therefore, remain active landscapes where the Earth's interior still participates directly in shaping the living world above it. Far below the last trace of daylight, another source of energy sustains the living landscape. It does not arrive from the sky, nor does it depend upon seasons, clear water, or the turning of the earth. Here, the foundation of life begins with chemistry itself. Mineral-rich fluids and methane rising through the lake floor become the starting point for an ecosystem that continues without a single ray of sunlight, revealing that Baikal possesses one more world concealed within its immense depth. Chemosynthesis is the process through which certain bacteria transform inorganic chemicals into organic matter. Instead of drawing energy from sunlight through photosynthesis, these microscopic organisms harvest chemical energy from methane, sulfur compounds, and minerals carried upward by hydrothermal activity. The result is living tissue created entirely without light. The process has long been recognized in the deep ocean, where hydrothermal vents support communities thriving thousands of feet beneath the surface in permanent darkness. For many years, scientists believed this remarkable strategy belonged almost exclusively to the oceans. Around marine hydrothermal vents, chemosynthetic bacteria support tube worms, clams, shrimp, crabs, and countless other organisms that never experience daylight. Every predator, scavenger, and grazer in those remote environments ultimately depends upon bacteria capable of transforming chemistry into food. It is an elegant solution to life in places where photosynthesis can never occur. Lake Baikal revealed that a remarkably similar pattern had emerged in freshwater through an entirely separate evolutionary path. Around methane seeps and hydrothermal vent fields, dense communities of chemoautotrophic bacteria spread across the sediment as living microbial mats. These mats appear as textured carpets covering portions of the lake floor, each layer composed of countless microorganisms continuously processing dissolved chemicals carried upward from deep within the Earth's crust. Their existence marks the beginning of a complete biological network independent of sunlight. Small invertebrates gather where these bacterial mats flourish. Amphipods feed directly upon the microbial growth, while leeches and other bottom-dwelling animals consume both the bacteria and the creatures already grazing there. Larger predators then hunt these invertebrates, extending the chain one level after another. Every transfer of energy can be traced back to chemical reactions occurring beneath the sediment instead of photosynthetic organisms floating near the surface. The architecture closely resembles deep ocean vent ecosystems, even though it arose within fresh water under entirely separate conditions. One feature makes this hidden community especially unusual. Most deep lakes gradually lose oxygen with increasing depth until their deepest waters can no longer support many oxygen-dependent organisms. Baikal follows a different pattern. Seasonal mixing continues, delivering oxygen throughout the entire water column, reaching even the deepest basin. As a result, organisms requiring abundant oxygen occupy the same environment as microorganisms drawing energy from chemical reactions. These contrasting biological strategies operate side by side, creating a layered ecosystem unmatched in any other known freshwater lake. Scientists suspected such communities might exist long before they could prove it, Direct confirmation required a journey to the bottom itself. During the summer of 2008, researchers descending into the deepest reaches of Lake Baikal observed these vent associated habitats firsthand. Their expedition transformed informed speculation into documented reality. The deepest floor of the world's oldest lake was no barren wasteland. It supported a functioning ecosystem built upon chemistry, preserving an evolutionary experiment that had unfolded unseen for millions of years beneath waters that appeared, from the surface, perfectly ordinary. The deepest floor of Lake Baikal remained an idea for far longer than it remained a destination. Maps ended where measurements faded into uncertainty, leaving scientists to estimate the shape of a world no human eyes had directly observed. Instruments had traced outlines through sound and calculation, yet the final descent still belonged to imagination until a pair of research submersibles prepared to carry people into the oldest freshwater abyss on Earth. On July 29th, 2008, researchers from the P. Shirshov Institute of Oceanology began that journey aboard the MIR-1 and MIR-2 submersibles. These were the same remarkable vessels that had previously explored the interior of the Titanic wreck deep beneath the Atlantic Ocean. Their engineering had already proven capable of surviving enormous pressure beneath salt water, but Baikal presented a different challenge. Freshwater provides less natural buoyancy than the ocean, altering how a deep diving craft behaves during descent and ascent. Engineers therefore approached the expedition with caution. Before committing to the lake's deepest basin, the crews completed nearly a full week of progressively deeper test dives, reaching approximately 1,300 feet, while carefully evaluating the handling characteristics of the submersibles in freshwater conditions. Every successful descent refined calculations, confirmed equipment performance, and prepared the team for a plunge beyond any previously visited point in the lake. The expedition had expected to arrive at a maximum depth of roughly 5,370 feet, matching the accepted scientific estimate. Instead, the instruments continued downward. The lake floor finally appeared at approximately 5,512 feet, more than 100 feet deeper than anticipated. The discovery revealed that Baikal had concealed an even greater depth than generations of surveys had suggested. The deepest freshwater basin on Earth proved deeper still, extending beyond the limits of earlier calculations. Across the sediment, the explorers encountered a landscape unlike the featureless plain many had imagined. Cone-shaped mud volcanoes rose from the floor, where methane-rich sediments had been pushed upward by gas pressure building beneath the lake bed. Nearby, active methane seeps released streams of bubbles that escaped directly from the mud before beginning their long ascent through the water column. Low-temperature hydrothermal seep structures appeared across portions of the basin, surrounded by dense microbial mats, already recognized as the foundation of an unusual ecosystem. One particularly important mud volcano received the name St. Petersburg from the expedition team. Resting at approximately 4,600 feet, it became one of the best documented geological features discovered during the mission. Scientists also recovered methane gas hydrate samples from the sediment. This marked the first successful collection of gas hydrates from any freshwater lake, demonstrating that Baikal stored substantial quantities of methane within pressure-stabilized crystalline deposits beneath its floor. The expedition itself never escaped the influence of the lake. During operations, a powerful storm crossing the surface damaged one of the support systems by breaking a propeller, briefly interrupting the work and reminding the team that conditions above remained as demanding as those below. Following the series of expeditions completed between 2008 and 2010, systematic exploration slowed dramatically. Much of Baikal's deepest landscape has therefore never been revisited, leaving broad stretches of its floor still waiting beyond the reach of direct human observation. Every layer resting beneath Lake Baikal carries the memory of a vanished world. Long after living creatures disappeared from the surface, traces of their existence drifted downward through the water, settling onto the floor one season after another. Leaf fragments, grains of pollen, volcanic ash, microscopic shells, wind-blown dust, and dissolved chemicals accumulated with remarkable patience. Nothing hurried the process. Year after year, century after century, the lake preserved each new page without erasing the ones already written below. The sediment filling the rift basin now extends for more than 4 miles beneath the lake floor. This immense archive began forming when the continental crust first fractured roughly 25 million years ago. While the basin continued sinking through geological time, fresh material settled above the older deposits, creating an uninterrupted sequence unlike any other found within a freshwater lake. Each layer marks a moment in Earth's environmental history, arranged in the same order the events originally occurred. Many lakes fail to preserve such complete records. Burrowing animals churn younger sediments into older ones. Rivers reshape the bottom through powerful floods. Earthquakes fracture deposits or remove entire sections from the sequence. Some lakes eventually fill with sediment altogether, erasing much of their earlier history. Baikal escaped these interruptions. Its continuously subsiding basin created room for fresh accumulation while protecting earlier deposits from widespread disturbance. The result is the longest known undisturbed sediment archive preserved within any lake on the planet. Scientists drilling into this remarkable column have recovered pollen from forests that disappeared millions of years ago. Each grain serves as evidence of plants that once covered landscapes stretching across Central Asia. By identifying these ancient species layer after layer, researchers reconstruct climates that existed long before human observation. Forests expanded, retreated, transformed into grasslands, and returned again. Their changing distribution recorded through microscopic particles that settled into the lake with every passing season. Volcanic eruptions also left unmistakable signatures within the sediments. Fine ash carried across Asia descended onto Baikal's surface before becoming sealed into distinct layers. Because many eruptions can be dated with exceptional precision, these ash horizons provide reliable time markers throughout the sediment column. Geologists use them to synchronize environmental records from different regions, refining broader geological timescales that support research extending far beyond Siberia itself. The chemistry preserved between those visible layers reveals even more. Tiny variations in minerals, organic compounds, and naturally occurring isotopes preserve evidence of ancient atmospheric carbon dioxide concentrations, shifts in surface water temperature, and changing patterns of rainfall over immense spans of time. These chemical fingerprints allow scientists to reconstruct climates that existed when few comparable records survived elsewhere. Each sample adds another fragment to the history of Earth's atmosphere and changing environments. The archive extends across extraordinary chapters of planetary history. It spans 5 major mass extinction events, records repeated advances and retreats of continental ice sheets, witnesses the gradual uplift of the Himalayas and preserves evidence for the expansion of vast grassland ecosystems across Central Asia. While continents shifted and countless species appeared before vanishing again, fresh sediment continued settling through Baikal's water without interruption, preserving those transformations in an orderly sequence. Today, researchers regard these sediment cores as among the most valuable geological materials ever recovered from a lake. Beneath thousands of feet of clear fresh water rests a planetary diary written in chemistry, minerals, and microscopic life. Only a small fraction has been carefully examined. Most of its pages remain sealed below the floor, preserving stories that have waited millions of years for someone to read them. Some lives are measured in days, others in centuries. The lineage of the Baikal sturgeon is measured in continental ages. Long before familiar mountain ranges rose across Asia, before flowering plants spread across much of the world, and before the dinosaurs reached the height of their dominance, ancestors of this remarkable fish were already moving through ancient rivers and shallow inland seas. Their descendants still glide across the floor of Lake Baikal, carrying a body design that has endured through nearly unimaginable spans of time. The Baikal sturgeon belongs to a lineage that first appears in the fossil record more than 200 million years ago. That places its ancestry before the supercontinent Pangaea had completed its separation into the continents recognized today. Entire oceans opened and closed while these fishes persisted. Countless branches of life emerged, flourished, and disappeared, yet the essential form of the sturgeon survived, adapting without abandoning the blueprint that had already proven remarkably successful. Paleontologists often describe such organisms as living fossils. The phrase does not suggest that evolution stopped working. Instead, it reflects extraordinary stability. Natural selection continued shaping every generation, refining physiology, behavior, and genetics while preserving the broad structure that consistently met the demands of its environment. The armored body, elongated form, sensory snout, and downward-facing mouth remained effective across changing climates and shifting ecosystems. Radical redesign offered little advantage when an existing solution continued performing exceptionally well. The age of this lineage becomes even more striking when compared with the surrounding landscape. The Himalayas, now the highest mountain range on Earth, began their major uplift roughly 50 million years ago and reached much of their dramatic elevation around 20 million years ago. By the time those mountains started climbing toward the sky, ancestors of the Baikal sturgeon had already existed for approximately 150 million years. Their history reaches into a chapter of Earth's past, so distant that the mountains themselves were still part of an unwritten future. Modern individuals remain impressive animals. Large specimens can reach lengths of approximately 6½ feet while weighing as much as 220 pounds. Their growth is deliberate, extending across decades rather than seasons. Many survive for 60 years or longer, following a pace of life that reflects patience instead of urgency. Such longevity accompanies slow maturity and infrequent reproduction, characteristics well suited to stable environments, but vulnerable when sudden human pressures appear. Feeding takes place along the lake floor, where the sturgeon searches through soft sediment with its distinctive rostrum, the broad paddle-like snout projecting ahead of its head. This structure serves as a highly sensitive probe, detecting prey concealed beneath the mud. Once food is located, the fish lowers its mouth and creates a powerful suction that draws mollusks, worms, and other buried invertebrates from the sediment. Each movement is deliberate, conserving energy while steadily gathering nourishment from the bottom communities supported by Baikal's complex ecosystem. Human history introduced challenges that geological history never had. Intensive fishing during the Soviet era reduced the Baikal sturgeon population so severely that natural recovery became increasingly difficult. Today, the subspecies is considered critically endangered in the wild. Artificial breeding programs now provide the primary means of sustaining its numbers, raising young fish before releasing them into the lake in hopes of preserving a lineage whose ancestry reaches back beyond nearly every familiar feature of the modern Earth. The sturgeon remains both an inhabitant of Baikal and a living reminder that deep time still swims beneath its waters. Movement across a landscape does not always end when the traveler arrives. Sometimes the journey continues in the shape of future generations, each one drifting a little farther from the path that brought its ancestors there. The Baikal Omul tells such a story. It entered this isolated lake from Arctic river systems during distant glacial ages, when waterways connected regions that now stand completely apart. Once inside Baikal, the fish encountered a world large enough to become many worlds at once. The Baikal Omul belongs to the whitefish family, sharing ancestry with salmon and Arctic char. Genetic evidence suggests that its forebears reached the lake through ancient drainage networks that existed during colder periods of Earth's history. As glaciers expanded and retreated, rivers changed direction, watersheds merged, then separated again. A population that entered Baikal remained behind when those connections disappeared, leaving the fish enclosed within a freshwater basin unlike any other on the planet. Isolation alone did not shape the Omul. The immense size and complexity of the lake offered opportunities unavailable in smaller freshwater systems. Some populations flourished in the open water, spending much of their lives suspended through the middle of the water column. Others favored the coastal shallows, following seasonal cycles close to the shoreline. A third group settled near the deeper bottom waters, exploiting resources rarely visited by their relatives. Each environment rewarded different habits, different feeding strategies, and different annual rhythms. Over millions of years, these populations gradually diverged. The pelagic race developed patterns suited to life in open water, where food sources and movement differed from those near shore. The coastal race adapted to changing conditions along the lake margins, while the near-bottom race became associated with deeper habitats. Their bodies, behavior, migration, timing, and diet all shifted in response to the particular demands of their chosen environments. Even so, they remain capable of interbreeding when their ranges overlap. That unusual balance makes the Omul especially valuable to evolutionary biology. The three races have not completed the journey toward becoming separate species, yet neither have they remained unchanged from their common ancestor. Scientists see within them a living example of speciation unfolding in real time. Genetic differences continue accumulating, while ecological specialization grows stronger. Baikal preserves the intermediate stages of a process that often becomes visible only after it has already finished. Human communities surrounding the lake have shared their own history with the Omul for centuries. Smoked Omul, prepared over open fires, became one of the defining foods of the Baikal region. Long before the Trans-Siberian Railway crossed the landscape, traders carried preserved fish along established routes linking distant settlements. The species nourished families, supported local economies, and became woven into regional tradition through countless ordinary meals. Heavy commercial fishing during the 1970s and 1980s pushed the Omul toward a severe population decline. The harvest grew beyond what natural reproduction could replace, forcing authorities to impose a fishing ban that lasted for decades. Only after monitoring showed signs of recovery did a limited commercial reopening begin in 2019. The OML continues serving another essential role beyond human culture. It transfers energy from tiny drifting organisms, including Epicura and amphipods, upward through the food web until that energy ultimately sustains the Nerpa, binding together the living layers of Lake Baikal through one enduring thread. Winter does not arrive here as a season of rest. It reshapes the entire lake into another world, one governed by different patterns of movement, light, and survival. Across the enormous basin, water that carried waves through summer gradually hardens into a single continuous roof of ice. From January through May, that frozen cover stretches across a lake nearly 397 miles long and as much as 50 miles wide. In many places, the ice grows close to 3 feet thick, strong enough to bear extraordinary weight while the living lake continues beneath it. The surface differs from the cloudy ice that forms on ordinary rivers and ponds. Baikal's winter cover is remarkably transparent, allowing sunlight to pass through with unusual efficiency. Beneath that frozen ceiling, specialized algae continue gathering energy from the filtered light. They have evolved to flourish under conditions that would leave most freshwater plants unable to grow. The ice softens and scatters the sunlight, creating a dim world where photosynthesis continues through the cold months, sustaining the first steps of a food web that never truly stops. Far below, methane released from geological seeps keeps rising toward the surface. Once the lake has frozen, that gas becomes trapped beneath the ice, forming pale spheres and vertical clusters suspended within the crystal clear sheet. Each frozen pocket marks a journey interrupted before the gas could escape into the air. Across wide stretches of the lake, these white formations create patterns unlike those recorded anywhere else on Earth at comparable scale, preserving a meeting between geology and winter in solid form. Although the ice seals the lake away from direct contact with the atmosphere, life below does not lose its supply of oxygen. As surface water cools, it becomes denser and sinks, carrying dissolved oxygen downward through the immense water column. This winter circulation continues, feeding the deepest habitats, allowing animals and microorganisms to remain active even at extraordinary depth. In many large lakes, the deepest water gradually loses oxygen over time, yet Baikal maintains conditions that support complex life from the surface to the bottom throughout the frozen season. The Nerpa depends completely upon this transformed landscape. Throughout winter, each seal maintains several breathing holes, scratching upward through the ice with specialized claws whenever fresh openings are needed. Those holes become reliable gateways between air and water, visited again and again across territories, remembered through instinct and experience. During March and April, pups enter the world upon the ice itself. Their white natal fur blends naturally with snow, a trait inherited from distant Arctic ancestors that continues serving its purpose in this inland lake. Young seals rely entirely upon the frozen platform during their earliest weeks, making the timing of spring melt deeply important to their survival. As warmer days gradually loosen winter's grip, the ice begins to fracture and drift apart. Sunlight pours more freely into the water, awakening an immense bloom of diatoms and algae. Tiny grazing animals respond almost immediately, feeding upon this sudden abundance. Fish gather where that nourishment spreads, and the seals follow the fish. Every layer of the ecosystem answers the same seasonal signal, each living thread woven into another through rhythms refined across millions of years, until the lake exchanges its frozen face for open water once again. Long before maps assigned borders to this landscape, or researchers lowered instruments into its depths, people gathered along these shores with another way of understanding the water before them. Their knowledge did not grow from laboratory measurements or geological surveys. It emerged through generations of living beside the lake, watching its seasons, listening to its changing moods, and passing those observations into memory. The Buryat people came to know Baikal as something greater than a place. They knew it as the sacred sea. The Buryat are a Mongolic people whose history around Baikal stretches back thousands of years. Archaeological discoveries show that human communities occupied these shores during the Upper Paleolithic, more than 20,000 years ago. Across countless generations, families hunted, fished, traveled, and raised children within sight of the water. The lake became woven into language, ceremony, and identity until its rhythms shaped everyday life as naturally as the turning of the seasons. Within Buryat tradition, Baikal possessed its own will, voice, and presence. It was approached with the respect given to a living elder rather than an object to be owned. Travelers offered prayers before crossing its waters. Ceremonies acknowledged the lake as a powerful being capable of generosity as well as judgment. Songs and spoken blessings formed part of ordinary encounters with the shoreline, expressing a relationship built upon reciprocity instead of possession. To take from the lake without gratitude invited imbalance, for the sacred sea was understood to notice how it was treated. That relationship found one of its strongest expressions on Olkhon Island, the largest among Baikal's 27 islands. The island became one of the most important spiritual places in Buryat tradition, regarded as the dwelling place of powerful spirits and shamans. Even today, wooden poles, known as surge stand, decorated with blue and white ribbons, tied by visitors and descendants who continue honoring old customs. Each ribbon represents a gesture of respect carried forward across centuries, linking present lives with those who once gathered beneath the same open sky. Among the best-known Buryat stories is the tale of Angara, the only river flowing outward from Baikal. She was remembered as the daughter of the Great Lake, who fell in love with the mighty Yenisei River and fled to join him despite her father's wishes. In sorrow and anger, Baikal cast an enormous stone after her. That stone, known as Shaman Rock, still rests near the mouth of the Angara River, close to Irkutsk, giving enduring shape to a legend that blends geography with memory. Centuries later, scientists began describing Baikal as a remarkably self-regulating ecosystem sustained through interactions among geology, climate, chemistry, and thousands of living species. Limnology, the scientific study of inland waters, gradually revealed an intricate network of relationships maintaining the lake across immense spans of time. Although the language differed, the conclusion carried an unexpected echo of much older beliefs. The lake behaved as an integrated living system whose balance depended upon countless connected processes. Russian Cossacks reached Baikal during the 1740s, recording the lake within expanding frontiers of the Russian state. The Trans-Siberian Railway arrived generations afterward, followed by industrial development during the Soviet era. New names, technologies, and economies transformed the surrounding landscape, yet the older understanding never vanished entirely. Along the shores, ceremonies still continue, ribbons still flutter in the wind, and the sacred sea remains a living presence for those who have never believed it could be reduced to water alone. The story carried within Baikal is measured across millions of years, yet one chapter occupies scarcely more than a human lifetime. Geological forces opened the basin, evolution filled it with singular life, and generations learned to live beside its waters. During the 20th century, another force arrived with remarkable speed. Factories, railways, expanding settlements, and growing industry reached the shoreline, leaving marks that accumulated far faster than the lake could erase them. In 1966, construction began on the Baikalsk pulp and paper mill along the southern shore, despite repeated warnings from Soviet scientists. Those researchers already understood that Baikal owed its exceptional clarity and chemistry to an unusually delicate balance. Industrial production threatened precisely the qualities that made the lake unique. Their concerns did not halt the project. For decades afterward, chlorine-bleached pulp waste, dioxins, and other chemical effluent entered the southern basin, introducing substances that had never belonged within this ancient freshwater system. The southern basin proved especially vulnerable because its waters exchange more gradually with the broader lake than many other regions. Fine sediment settled across the floor, carrying contaminants into layers that now preserve a modern record, unlike the natural archive resting far below. Even after the mill ceased operations in 2013, much of that contamination remained. Chemicals bound within the sediment continue entering the surrounding water little by little, following rhythms measured across centuries instead of political terms or economic cycles. Closing the source ended one chapter, although it could not erase the material already woven into the lake itself. Human influence extends beyond the former mill. The Trans-Siberian Railway follows much of Baikal's southern shoreline, transporting freight that includes petroleum products. Every train passes beside habitats shaped through immense spans of natural history. Although safety measures have improved over time, the possibility of derailments and accidental spills remains a continuing concern because shoreline ecosystems recover far more slowly than industrial accidents unfold. Beyond transportation, surrounding landscapes have also changed. Agriculture across nearby parts of the Buryat Republic and the Irkutsk region contributes increasing amounts of nitrogen and phosphorus compounds to streams flowing toward the lake. Baikal evolved under extraordinarily nutrient-poor conditions, where even modest additions can alter ecological relationships. Algae that once remained carefully balanced may expand more readily, changing the availability of oxygen and influencing species that evolved within one of Earth's clearest freshwater environments. Evidence of modern civilization now reaches places far removed from roads or towns. During a research expedition conducted in 2020, scientists recovered microplastic fragments from the lake floor between 360 and 625 feet below the surface. Small pieces of packaging plastic had settled into deep water hundreds of miles from the nearest major industrial center. Their presence demonstrated that lightweight debris can travel through the atmosphere and watershed before descending into environments once considered almost unreachable. Tourism has also expanded steadily since the 1990s. More visitors bring appreciation for Baikal's beauty, while greater demand for roads, lodging, wastewater systems, and shoreline development introduces additional pressure to habitats that remained lightly disturbed for thousands of years. The lake still renews itself through extraordinary natural processes, yet every new burden asks more from a system whose greatest strength has always depended upon balance, patience, and time measured far beyond the length of a single human century. A forest can disappear without a single tree falling across the land. On the floor of Lake Baikal, the loss begins with color. Colonies that once spread across rock in branching forms gradually surrender their deep green hue. Gray replaces emerald, living tissue weakens, and structures that supported entire communities begin to crumble into pale remains. One of the oldest builders in the lake has entered a period of decline that no generation of scientists had witnessed before. Around 2011, researchers first noticed signs of an unfamiliar disease affecting Baikal's endemic freshwater sponges. These organisms had endured immense spans of geological change, surviving shifts in climate, tectonic movement, and evolving ecosystems. Their decline followed a different pattern. Bleaching spread across colonies. Healthy tissue broke apart through necrosis, and the damage advanced through sponge beds that had remained stable for countless generations. By the time the crisis was documented in scientific publications, broad areas along the western shoreline had already been affected, extending through shallow water and into middle depths where thriving sponge communities had long dominated the rocky lake floor. The transformation begins within the sponge itself. Its green color comes from microscopic algae living among its tissues in a close biological partnership. Those algae contribute nourishment while receiving shelter and access to sunlight filtered through Baikal's remarkably clear water. Rising water temperatures place increasing stress upon that relationship. As the algae fail, bacterial infection gains an opportunity to spread through weakened tissue. The sponge loses its color first, then its strength. Branches collapse, living surfaces decay, and what remains gradually hardens into lifeless mineral deposits, resting upon the rocks where vibrant colonies once stood. Each fallen sponge represents more than the loss of a single organism. These formations function as the physical framework of the lake floor, creating shelter, breeding sites, and feeding surfaces for dozens of endemic species. Juvenile fish find protection among their branches. Invertebrates cling to their surfaces, graze upon the microscopic life, coating them, and reproduce within their intricate structure. Mollusks living around sponge beds support the Baikal sturgeon, linking these colonies to one of the oldest fish lineages still swimming through fresh water. As sponge habitat disappears, every connected species encounters a landscape with fewer places to live, feed, and reproduce. Recovery unfolds according to biological rhythms that cannot be hurried. Healthy colonies require decades to expand into substantial formations, while the largest structures represent growth accumulated across far longer intervals. Once an established sponge bed has collapsed, there is no practical method capable of rebuilding it within a human lifetime. Restoration depends upon surviving colonies, favorable environmental conditions, and the gradual return of ecological relationships assembled piece by piece through natural growth. For many researchers, the bleaching crisis has become the clearest visible signal that Baikal's deep ecosystem is already responding to changes beginning far above the lake floor. Surface warming, altered water conditions, and biological stress now reach organisms that once appeared remarkably resilient. Monitoring programs continue documenting the progression, yet the changes often advance more rapidly than observations can fully capture. Across a lake shaped over millions of years, one of its oldest living foundations is fading, leaving empty spaces where intricate communities once gathered and where renewal proceeds according to the patient measure of geological time. Nothing in Lake Baikal appears to command attention less than the tiny crustacean drifting through its open water. Barely larger than a grain of rice, it spends its life suspended within the lake's immense interior, carried by currents that have flowed across this basin for millions of years. Yet the clarity of the water, the chemistry sustaining countless species, and the balance holding this extraordinary ecosystem together depend upon the uninterrupted work of this minute animal. Epicura survives only under remarkably stable conditions. Cold water, abundant dissolved oxygen, and an exceptionally consistent chemical environment have shaped its existence across immense spans of time. Baikal provided those conditions through repeated climatic cycles, allowing this crustacean to become one of the most influential organisms in the lake. Day after day, it feeds upon microscopic algae, bacteria, and suspended organic particles, continuously filtering the water surrounding it. Collectively, these tiny animals cleanse between 500 and 1,000 cubic miles of water each year, preserving the transparency that has become one of Baikal's defining characteristics. The environment supporting that balance has begun to shift. During the past century, average surface water temperatures have risen by about 1.5 degrees Fahrenheit, and observations indicate that warming has accelerated during recent decades. The greatest changes occur within the upper layers where sunlight reaches most readily, exactly where large populations of Epicura concentrate during much of the year. Monitoring programs have documented measurable declines in population density within these warming waters, suggesting that conditions once considered dependable are becoming increasingly difficult for this specialized crustacean to endure. As fewer individuals filter the water, subtle chemical changes begin spreading through the ecosystem. Microscopic algae and bacteria remain suspended for longer periods instead of being consumed. Greater biological growth gradually reduces water clarity while increasing the amount of organic material decomposing within the lake. That decomposition consumes dissolved oxygen and alters the chemical balance that countless endemic organisms have relied upon throughout their evolutionary history. Each change appears modest when viewed alone, yet together they reshape the environment, supporting nearly every level of life. The shoreline already reveals signs of this transition. Since the middle years of the first decade of the 21st century, filamentous green algae, known as Spirogyra, has expanded across coastal habitats where it was once only a minor presence. Rising nutrient levels encourage its growth, allowing dense mats to spread across rocks and smother communities that evolved under far leaner conditions. The weakening filtration provided by declining Epicura populations removes another natural restraint, giving these algae additional opportunity to occupy space that once supported a broader variety of endemic life. A deeper pattern emerges within these changes. Epicura maintains the clear, oxygen-rich water that Epicura itself requires. As warming reduces its abundance, water quality gradually shifts away from the conditions that favor its survival. Fewer crustaceans then remain to perform the filtering that restores balance, allowing the cycle to strengthen with each passing season. The consequences extend far beyond one microscopic species. Water, transparent enough for the Nerpa to pursue prey by sight, oxygen carried to depths approaching 5,000 feet, and the chemical stability that allowed millions of years of specialized evolution all rest upon the steady labor of an animal almost invisible to the human eye. Across Baikal, one of the greatest ecological foundations has always been among its smallest inhabitants. A map can show where a lake begins and where its shoreline ends, yet no map reveals the invisible boundary that shaped the lives within it. Once a lineage crossed into Baikal and became isolated from the outside world, another journey began. Generation followed generation until descendants no longer resembled the travelers that first entered these waters. Time transformed separation into creation, and the lake became an evolutionary world unto itself. A species is called endemic when it exists in one place and nowhere else on Earth. Many lakes contain a handful of such organisms, usually between 5 and 10% of their total species. These represent local variations on forms that still survive elsewhere in slightly different versions. Baikal tells an entirely different story. Among its 2,595 described animal species, about 80% exist nowhere beyond this single basin. Their disappearance here would mean their disappearance from the planet itself. The pattern extends beyond individual species. 11 entire families and subfamilies occur only within Baikal, along with 96 complete genera unknown from any other freshwater system. Such numbers reveal something larger than successful adaptation. They describe the steady formation of new evolutionary branches entirely inside the lake. Ancestors entered long ago, became separated from relatives beyond the watershed, and gradually diversified until descendants occupied nearly every ecological opportunity available, from wave-washed stones along the shore to sponge forests, open water, abyssal sediment, and communities surrounding hydrothermal seeps thousands of feet below the surface. Biologists recognize this process as adaptive radiation, the expansion of a single ancestral lineage into many forms suited to different ways of life. Few freshwater examples approach the scale preserved here. The amphipods alone illustrate the pattern with remarkable clarity. From what were once only a small number of Eurasian ancestors, more than 350 species evolved inside Baikal. Some became swift swimmers of open water, others crawled across rocky slopes, some scavenged organic debris, and others occupied depths where sunlight never reaches. Together, they demonstrate how isolation and opportunity can reshape an entire branch of life. A useful comparison comes from the Galapagos Islands, where isolated ancestors also diversified into forms found nowhere else. The resemblance lies in the evolutionary process rather than the landscape. Both systems limited outside gene flow while providing a variety of ecological roles waiting to be filled. Over immense spans of time, natural selection guided separate populations along different paths until each became uniquely suited to its own surroundings. Baikal repeated that experiment beneath fresh water instead of across volcanic islands, producing an equally remarkable catalog of biological innovation. Looking across the lake today means looking at familiar ecological roles carried out by unfamiliar actors. Predators, grazers, scavengers, filter feeders, burrowers, and parasites all exist, yet the species performing those tasks belong almost entirely to lineages found nowhere beyond these shores. Evolution solved the same environmental challenges that appear across the rest of the world, although it wrote its answers using different living forms. Baikal, therefore, represents more than exceptional biodiversity. It preserves the outcome of a parallel evolutionary experiment conducted across 25 million years of uninterrupted isolation. The same natural laws operated here as everywhere else, yet the life they produced became a singular expression of possibility, existing without duplicate, replacement, or second beginning anywhere on Earth. There comes a point when a single place begins speaking beyond its own shores. Baikal reaches that point through patterns repeated across living communities that never shared a common origin. The lesson does not remain confined to one lake in eastern Siberia. It extends into a broader understanding of how life responds whenever the physical world presents the same enduring challenges. Researchers studying Baikal's deepest habitats have long recognized similarities that reach far beyond appearance. Pressure-adapted amphipods occupy ecological roles strikingly similar to those of crustaceans living in the deepest parts of the oceans. The Golomyanka drifts through dark water much as mesopelagic fishes do in marine environments, rising and descending through the water column as food and energy move above and below. Around hydrothermal vents, communities organized around chemical energy resemble those surrounding oceanic vents, with specialized organisms gathering where dissolved minerals emerge from the Earth's interior. The architecture of these ecosystems echoes one another, despite developing in complete isolation. Those resemblances did not arise because the lake inherited its inhabitants from the deep sea. The lineages are only distantly related, separated by immense evolutionary history. Biologists describe this pattern as convergent evolution, the process through which unrelated organisms independently arrive at similar solutions because they experience comparable environmental pressures. Evolution did not copy an earlier design. It reached a similar destination through an entirely separate journey, beginning with different ancestors and following different genetic pathways across millions of years. The conditions shaping those outcomes remain remarkably consistent. Darkness limits vision regardless of whether the water is fresh or salty. High pressure influences bodies in similar ways, wherever great depth exists. Cold temperatures slow metabolism and favor efficient use of energy. Hydrothermal vents provide chemical compounds that sustain life without depending upon sunlight. When these ingredients remain stable across immense spans of time, natural selection repeatedly favors traits that succeed under those circumstances. Distinct evolutionary histories gradually produce ecosystems whose overall structure appears surprisingly familiar. This realization carries consequences extending well beyond the study of Baikal itself. Extreme depth does not require an ocean before life discovers workable solutions. The physical environment establishes the challenges, and evolution explores countless variations until effective strategies emerge. Similar ecological roles appear again because they answer the same practical demands. Predators, scavengers, filter feeders, decomposers, and organisms sustained by chemical energy become parts of an integrated community, even when none of the participating species share close ancestry with their counterparts elsewhere. The pattern also reshapes the way scientists think about the limits of biology. Adaptations, once considered distinctive to marine abysses, are revealed as broader biological responses that can emerge wherever comparable conditions persist. Evolution proves more flexible than the identities of individual species. Lineages differ, histories diverge, yet the physical world continues presenting familiar problems, and living systems continue discovering workable answers through variation and natural selection. Seen from that perspective, Baikal becomes more than an exceptional freshwater lake. It stands as a demonstration that environment exerts a profound influence over the direction of evolution. Given enough time, stable conditions, and opportunities for natural selection to operate, life repeatedly constructs comparable ecological frameworks from entirely different beginnings. The organisms differ, their ancestry differs, and their histories remain separate, yet the living systems they assemble reveal the same enduring conversation between biology and the physical world. Far from the frozen shoreline, another connection begins to emerge, one that reaches beyond Earth itself. The deepest communities of Baikal are no longer studied only to understand a remarkable lake. They have become a guide for imagining places where no human has yet stood, places where darkness, water, rock, and heat may have worked together for ages beyond counting. One destination is Europa, a moon of Jupiter covered by an immense shell of ice. Evidence gathered across decades of observation indicates that a global ocean lies beneath that frozen exterior. No sunlight reaches those waters. The ocean is believed to rest against a rocky floor, while Jupiter's gravitational pull continually flexes the moon, generating heat within its interior. Another destination is Enceladus, a moon of Saturn. Observations from the Cassini spacecraft confirmed towering plumes of warm water escaping through fractures in the ice, revealing a subsurface ocean supplied by active hydrothermal processes below. Although separated by extraordinary distances, these environments share a striking collection of physical conditions with the deepest parts of Baikal. Each contains liquid water isolated from sunlight. Each possesses a rocky or sediment-rich foundation capable of supporting chemical reactions. Each offers the possibility that heat rising from within can deliver dissolved minerals into surrounding water. Those ingredients form the same basic setting where Baikal's chemosynthetic communities have demonstrated that complex ecosystems can persist without depending upon light from the surface. That realization transformed scientific thinking. Hydrothermal ecosystems were once regarded primarily as products of the deep ocean, requiring marine chemistry and immense planetary seas. Baikal revealed another possibility. Within an enclosed freshwater basin, separated from the oceans for millions of years, chemical energy, rising through the lake floor, supported organisms organized around remarkably similar ecological principles. The water differed. The evolutionary histories differed. The underlying process remained recognizable because the physical conditions imposed comparable demands upon life. The significance extends beyond comparison alone. Convergent evolution has already shown that unrelated organisms repeatedly discover similar biological solutions when confronted with similar environments. Baikal strengthens that principle by demonstrating it across entire ecosystems. If darkness, pressure, chemical energy, and stable liquid water consistently produce comparable ecological structures on Earth, those same conditions elsewhere become more compelling places to search for life. The expectation is grounded in observed biology, not in imagination alone. For that reason, missions planned by the National Aeronautics and Space Administration and the European Space Agency frequently draw upon Earth's natural analogs when preparing instruments and scientific objectives. Baikal's vent communities stand among the environments most often examined because they represent one of the closest accessible examples of an enclosed, ice-influenced, hydrothermally active body of water supporting diverse organisms through chemical energy. The lake offers practical lessons for recognizing biological signatures that may emerge beneath distant ice-covered worlds. Its importance, therefore, reaches beyond geography. Baikal preserves evidence that life can flourish where sunlight never arrives, provided another source of energy remains available across immense spans of time. That insight reshapes the search for living worlds. The deepest water of one Siberian lake has become a reference point for oceans circling distant planets, suggesting that wherever enduring physical conditions resemble those found here, biology may again discover a path toward complexity, written through different organisms, yet guided by the same enduring laws of nature. Maps often suggest completion. They outline shorelines, trace mountain ranges, and measure depth with careful precision. Baikal appears thoroughly documented when viewed from above, yet that impression fades as attention turns toward the water below. Even after centuries of observation, the lake continues withholding much of its living world, reminding science that exploration is not measured only by distance traveled, but by how much remains beyond direct knowledge. The catalog of life within Baikal currently includes approximately 2,595 described animal species. Researchers regard that number as a beginning rather than a final count. Sampling has reached only a limited portion of the deepest regions, where immense stretches of the lake floor remain difficult to visit and even harder to study repeatedly. Every expedition explores only a small fraction of an environment extending thousands of feet below the surface, leaving broad areas represented by scattered observations instead of continuous records. Unexpected discoveries often arrive while scientists are pursuing entirely different questions. During the 2020 expedition that investigated microplastic contamination, recovered fragments of discarded plastic carried living passengers. Attached to their surfaces were previously undescribed bryozoans, leeches, and fungal like organisms that had escaped notice until human debris provided an accidental collection platform. The discoveries emerged through contamination research, revealing that unfamiliar life still waits in places examined for unrelated purposes. Genetic analysis has widened that sense of uncertainty even further. Sediment gathered from the deep floor contains genetic sequences that cannot yet be matched with any known organism. Those traces confirm the presence of living forms whose appearance, behavior, ecological relationships, and evolutionary history remain entirely uncharacterized. Their existence is recognized through molecular evidence alone, while the organisms themselves continue beyond direct observation. In some cases, science has detected their biological signature before encountering the creatures that produced it. The archive beneath the lake deepens the mystery. Nearly 4 miles of accumulated sediment preserve an uninterrupted environmental history reaching back approximately 25 million years. Only a handful of drilling locations have penetrated this extraordinary record. Most of the buried archive remains untouched, preserving chemical histories, fossil pollen, microscopic organisms, and geological events that have never been sampled. Countless chapters of Earth's environmental past still rest where they formed, unread and undisturbed. Even familiar inhabitants continue guarding parts of their story. The Golomyanka, the most abundant fish in Baikal by total weight, spends much of its existence at depths that visiting submersibles have explored only briefly. Important aspects of its movements, behavior, and reproduction have never been directly witnessed. The proposed migration route that eventually brought the Nerpa seal into the lake also remains a hypothesis, supported by evidence yet lacking a continuous fossil record that traces every stage of the journey. Large portions of the lake floor share that same uncertainty. Mapping expeditions completed between 2008 and 2010 documented only part of the benthic landscape. Most of the bottom has never been photographed, sampled, or described in detail. In the most literal sense, humanity still cannot say with certainty what lives across much of Baikal's deepest floor. After millions of years, shaping its own living world, the lake continues, offering discoveries to those willing to descend, observe, and accept that the greatest remaining frontier may rest beneath fresh water rather than beyond the horizon. Isolation does more than preserve life. Given enough time, it reshapes possibility itself. Within Baikal, evolution unfolded inside boundaries that remained remarkably stable for millions of years. The lake became less like a crossroads and more like a workshop, where each lineage refined its place generation after generation until the inhabitants bore little resemblance to the ancestors that first entered its waters. Across rivers, lakes, and connected watersheds elsewhere, species rarely exist without interruption from newcomers. Fresh competitors arrive, predators expand their range. Generalists capable of thriving under many conditions spread into fresh territory, often displacing organisms with narrower requirements. Ecological balances shift repeatedly as climates change and waterways reconnect. Such continual mixing favors flexibility, rewarding creatures that can adapt to many circumstances instead of becoming highly dependent upon only one. Baikal followed another path. Its long isolation greatly reduced the arrival of outside lineages, allowing evolution to proceed almost entirely among residents already present. Competition remained intense, yet it unfolded within the same community rather than against an endless succession of newcomers. Every available ecological opportunity encouraged gradual refinement instead of replacement. Species responded by dividing resources with increasing precision, each occupying a role that differed ever more subtly from those around it. The results can be seen throughout the lake. The Golomyanka expanded into nearly the entire water column, occupying a combination of depths unmatched by any other freshwater fish. Amphipods diversified into approximately 350 distinct species, partitioning the lake floor into countless ecological roles that once belonged to only a few ancestral forms. The tiny crustacean Epicura became overwhelmingly dominant among the zooplankton, accounting for approximately 96% of that community and supporting the chemical balance upon which countless other organisms rely. Evolution produced specialization, layered upon specialization, until nearly every ecological space possessed its own resident expert. Such refinement carries a profound consequence. As organisms become precisely matched to one environment, they also become increasingly difficult to replace. A specialist shaped over millions of years performs tasks that no generalist can easily assume. Remove that organism, and the surrounding community loses more than a single species. It loses relationships, energy pathways, and biological functions built around a partner that evolved alongside every neighboring form. This process resembles biological fine-tuning across immense spans of time. Each generation preserved slight variations that fit Baikal's particular conditions more effectively than those before. Small advantages accumulated until extraordinary adaptations emerged. These creatures became exceptionally successful inside one lake while surrendering much of their ability to thrive elsewhere. Their strengths are inseparable from the environment that shaped them. The Golomyanka illustrates this dependence with striking clarity. Its body, rich in oil and adapted for cold darkness, deteriorates rapidly when exposed to sunlight and warmer conditions. Throughout its evolutionary history, no persistent pressure favored structures capable of enduring life near the surface. Energy remained devoted to surviving the depths where the species spent nearly its entire existence. The Nerpa carries another inheritance. Its pups are born with white fur upon winter ice, a pattern reflecting millions of years of ancestry linked to frozen northern environments where concealment offered protection. Around Baikal, natural land predators hunting from above never impose the same selective force, yet the behavior endured across countless generations. These characteristics are not flaws. They reveal what prolonged isolation can accomplish when evolution is allowed to elaborate without interruption, shaping organisms whose identities become inseparable from the singular world that created them. Perfection in nature carries a hidden cost. A living system, refined across immense spans of time, gains remarkable precision, yet that same precision narrows the range of conditions it can endure. Baikal's inhabitants reveal this truth with unusual clarity. Their extraordinary adaptations emerged within an environment that changed so gradually that evolution favored refinement over flexibility, leaving many species exquisitely fitted to one place and one set of conditions alone. Ecologists have long recognized that the organisms facing the greatest risk of extinction are often those that appear most successful within their native habitats. Specialists devote millions of years to mastering a particular environment until nearly every feature of their biology reflects its demands. Such precision leaves little capacity for abrupt adjustment. A modest shift in temperature, chemistry, or available food may exceed limits that remained unchallenged throughout countless generations. For most of its history, Baikal offered remarkable consistency. Its waters remained cold, exceptionally clear, rich in dissolved oxygen, low in nutrients, and chemically stable across intervals so long that entire evolutionary lineages arose without experiencing the rapid environmental swings common elsewhere. Each generation inherited conditions closely resembling those before it. Selection therefore rewarded increasing efficiency within that dependable world, instead of preparing organisms for dramatic change. The tiny crustacean Epichura embodies this dependence. Its physiology functions within Baikal's distinctive combination of temperature, dissolved oxygen, and water chemistry. It cannot abandon the lake for warmer or murkier waters because no neighboring freshwater system offers the conditions that shaped its evolution. Beyond those narrow limits, the biological machinery that allows it to filter immense volumes of water ceases to function effectively, removing one of the principal foundations supporting the lake's remarkable clarity. The Golomyanka faces another expression of the same challenge. Its body contains abundant oil, while its nearly transparent skin and patterns of movement evolved in persistent cold and darkness. Rising temperatures disturb the timing of its vertical migrations, alter its reproductive rhythm, and affect the metabolism upon which its unusual physiology depends. These changes emerge without requiring dramatic warming. Even gradual shifts influence processes that evolved under conditions of exceptional stability. The freshwater sponges reveal how closely disease and environment can become intertwined. The bacteria associated with recent bleaching events were not entirely new arrivals. Colder water had long limited their impact, preserving the delicate partnership between sponge tissues and the microscopic algae living within them. As temperatures rise, that balance weakens. The algae becomes stressed, the protective relationship begins to fail, and bacterial infection spreads through colonies that once persisted across decades with little interruption. Many widespread freshwater fish display broader tolerance. Carp, pike, and common freshwater perch endure warmer summers, fluctuating nutrients, declining water clarity, and changing habitats without immediate collapse because their evolutionary histories favored versatility. Baikal's endemic organisms followed another trajectory. They invested generation after generation in perfect adaptation to one extraordinary lake, surrendering resilience beyond its boundaries. This is the enduring paradox, shaped by approximately 25 million years of uninterrupted isolation. Stability allowed evolution to create one of Earth's most distinctive freshwater ecosystems, filled with organisms of unmatched refinement and precision. Those same qualities now define its greatest vulnerability. The closer each species came to fitting Baikal perfectly, the fewer pathways remained for surviving a world that no longer behaves as it once did. At this very moment, the lake continues without interruption. No announcement marks the passing of another hour beneath its surface. No signal declares the beginning of another cycle. Across the Great Basin, countless living processes unfold exactly as they have through ages beyond memory, following rhythms established long before human history entered the landscape surrounding these waters. Far below several feet of Siberian ice, a Golomyanka begins its nightly ascent. It rises through complete darkness, following drifting concentrations of zooplankton toward higher water. Pressure changes guide its movement with remarkable precision, allowing the fish to navigate an environment where light has no role. Its transparent body carries the adaptations refined across millions of years, each movement repeating patterns inherited through generations that never encountered nets, engines, or artificial light. Elsewhere, a Nerpa glides downward into the depths. With a single breath, it descends beyond 1,000 feet, its heartbeat slowing as stored oxygen sustains muscles built for prolonged dives. Around it stretches water of extraordinary clarity, often allowing visibility approaching 130 feet. Vision remains useful, even at remarkable depth, giving the seal confidence within a realm that rewards patience more than speed. Across the lake floor, amphipods continue their constant labor. Some graze upon organic fragments resting on the sediment. Others search for carrion, carried by faint currents. Predators pursue smaller relatives across the bottom, maintaining relationships that have persisted since long before the appearance of our own species. Every encounter contributes to an ecosystem that has remained active through glacial cycles, volcanic change, and the gradual reshaping of continents, never requiring an audience to continue. Not far away, methane rises through sediments in streams of tiny bubbles. Under immense pressure and persistent cold, portions of that gas become crystalline hydrates before reaching higher water. This transformation has continued across spans of time measured in millions of years, repeating through conditions that remained remarkably stable. Around these vent fields, microbial communities convert chemical energy into living tissue, assembling organic compounds from inorganic materials without depending upon sunlight. The process unfolds continuously, sustaining life where photosynthesis cannot reach. None of these organisms recognizes warming water as an abstract concept. None perceives the spread of sponge disease, the gradual decline of epicura, or fragments of plastic resting hundreds of feet below the surface. Each creature responds only to the immediate conditions surrounding it. The lake itself offers no judgment and no urgency. Biological systems continue operating with the mechanisms evolution provided, following instructions written across approximately 25 million years of uninterrupted persistence. Within that persistence lies both resilience and vulnerability. Baikal does not hasten its recovery when conditions deteriorate. It cannot compress centuries of ecological repair into a single season, nor can it negotiate with disturbances arriving faster than evolution prepared it to withstand. The living system proceeds at the pace established by geology, climate, and deep time. Tonight, as on countless nights before, the lake continues its work with unwavering consistency, carrying forward a world whose measure has always been millions of years rather than the brief passage of human generations. Some places invite measurement before they invite reflection. Baikal does both at once. Every expedition adds another chart, another sample, another sequence of observations. Yet beneath those discoveries rests a quieter realization. This immense freshwater world reached completeness long before any human understood it existed in more than outline, and it continued without interruption while entire civilizations appeared, flourished, and disappeared far beyond its shores. For millions of years, the Nerpa descended through dark water to depths approaching 1,300 feet. The Golomyanka carried out its nightly migration through the water column, rising and falling with dependable rhythm. Amphipods spread across the lake floor, feeding, hunting, recycling, and shaping the sediment beneath them. None of these patterns began when people arrived. Each belonged to a history extending far beyond memory, continuing through approximately 25 million years without requiring witnesses. Human knowledge entered this story only in fragments. The Golomyanka remained undescribed until the 19th century, despite being among the most abundant fish in the lake by weight. No expedition reached the absolute bottom until 2008. Even after that achievement, most of the benthic landscape remained unexplored. Immense regions of the floor have never been photographed, sampled, or examined directly. Their communities continue existing beyond the edge of observation, carrying forward relationships established across geological time. That realization reaches beyond biology. Entire vent communities converted chemical energy into living tissue. Sponge gardens expanded across rocky surfaces. Food chains linked microscopic organisms with larger predators through intricate exchanges of energy. Every cycle operated in full, complete, and uninterrupted, despite existing entirely outside human awareness. Nothing about those systems depended upon being discovered. They neither accelerated nor changed when attention finally reached them. This separates Baikal's depths from the ordinary idea of wilderness. Wilderness often describes landscapes that humans have not substantially altered. The deepest reaches of this lake represent something different. They formed a complete world that people had not even entered. Its inhabitants evolved, reproduced, diversified, and filled ecological roles in places where no human presence existed to observe success or failure. The distinction carries unusual weight because it reminds us that existence itself has never depended upon recognition. The lake, therefore, offers more than evidence about evolution or geology. It invites reflection upon humanity's place within a much larger living reality. Knowledge expands steadily, yet every new expedition reveals additional questions waiting beyond the last survey line. Discovery becomes less like completing a map and more like opening another doorway into an older landscape that never paused while we searched for it. Perhaps that is the deepest lesson resting beneath Baikal's waters. A complete and self-sustaining world endured through millions of years before anyone imagined its full extent. Even now, unseen organisms continue their lives beyond the reach of routine exploration, following the same physical laws that shaped every ecosystem described throughout this journey. Somewhere beyond familiar maps, other enclosed worlds may already be unfolding with equal independence, guided by darkness, pressure, chemistry, and time, existing entirely on their own terms, whether humanity ever reaches them or not. Nothing within Baikal waits for an ending. Every process already belongs to a story still unfolding, measured across intervals so large that human generations pass like brief weather. The lake keeps its own calendar, one written in shifting rock, circulating water, and living lineages that continue adapting whether they are observed or left entirely alone. Deep beneath the basin, the continental rift remains active. This year, it widens by about 0.8 inches. Next year, it will widen again by nearly the same amount. The movement is almost impossible to notice within a single lifetime, yet it never truly stops. Grain by grain, fracture by fracture, the basin deepens while its rocky walls drift farther apart. The geological sentence that began approximately 25 million years ago is still being written, each passing year adding another nearly invisible line. Project that movement far enough into the future, and an entirely different landscape begins to emerge. If the present trajectory continues across tens of millions of years, the Asian continent may eventually divide along this growing rift. Ocean water could enter the expanding basin, transforming today's freshwater lake into a shallow sea. The process would resemble the long evolution that shaped the Red Sea, another young ocean basin still progressing through the earliest chapters of its formation. Such changes unfold so gradually that no single generation could witness more than an immeasurably small fraction of the transformation. Life would continue changing alongside the geology. The Golomyanka would not remain exactly as it exists today. Countless generations would reshape its body in ways impossible to predict from the present. The Nerpa lineage might encounter expanding connections to salt water, following evolutionary pathways unlike any it has known since becoming isolated within the lake. Amphipods, descendants of creatures already astonishing in their diversity, could expand into newly formed marine habitats, carrying familiar biological patterns into environments that do not yet exist. Another future remains equally grounded in reality, although its timescale is profoundly different. Rising temperatures, declining populations of Epicura, widespread sponge loss, altered nutrient cycles, and accumulating ecological stress could push the lake beyond important biological thresholds within a human lifetime. If those changes reinforce one another, an ecosystem assembled through approximately 25 million years of gradual refinement could lose much of its extraordinary complexity within only a few decades. Evolution creates remarkable systems, yet ecological disruption often unfolds far more rapidly than their recovery. Both possibilities belong to the same lake. Neither requires intention from the water, the rocks, or the living communities they sustain. Baikal does not choose among futures. It continues operating according to physical laws and biological processes that remain indifferent to hope, fear, expectation, or memory. The Nerpas continue diving. The ghost fish continue rising through dark water. Ancient sponges persist where conditions still permit their growth. Every cycle proceeds, one moment after another. Above, the winter ice groans as pressure reshapes its frozen surface. A narrow beam of sunlight reaches unexpectedly deep, touching a Golomyanka before fading into blue water. Across the lake floor, amphipods continue their patient work without interruption. The lake carries forward its own enduring rhythm, and tomorrow it will begin again exactly where today has left it. Depth can be measured with instruments, charted on maps, and written into records. Another kind of depth resists every calculation. It emerges only after following this lake, through its history, its creatures, and its patient geology, until one quiet realization remains. The deepest thing about Baikal has never been the distance from its surface to its floor. It is the understanding that the world continues becoming itself whether anyone has witnessed it or not. People first recorded this lake in 1643. They crossed its frozen surface, traveled along its shores, caught its omul, rendered the oily flesh of the Golomyanka into lamp fuel, and gradually learned the habits of the Nerpa resting upon winter ice. Maps improved, expeditions returned, generations added observations, measurements, and names. Even so, the deepest point remained beyond direct human reach until 2008. 365 years passed between naming the lake and visiting its lowest floor, and that first encounter lasted only a brief moment compared with the immense history resting below. Even now, the picture remains unfinished. Most of the animals inhabiting the deepest regions have never been observed alive by human eyes. Much of the sediment preserving approximately 25 million years of environmental history, has never been sampled. Countless genetic signatures still belong to organisms without scientific names or descriptions. The question that drew us here remains open, not because evidence is lacking, but because the lake continues holding more than exploration has yet uncovered. What has already been revealed would have seemed impossible in almost any other freshwater system. A transparent fish spends its life suspended through the water column, its delicate body suited to darkness and cold. A seal carries the memory of distant marine ancestors while living entirely within fresh water. Hundreds of amphipod species divide one lake floor into hundreds of ecological roles, each refined through long isolation. Hydrothermal vents release chemical energy that nourishes living communities where sunlight never arrives. Every discovery belongs to the same enclosed basin, opened within a fracture, crossing the Asian continent, and shaped across approximately 25 million years of uninterrupted change. None of these living systems required an audience. Evolution unfolded without applause. Geological forces continued without observation. Microbial communities transformed chemistry into life long before language existed to describe either chemistry or life. Every generation inherited the conditions left by those before it, adding another small adjustment to a process stretching far beyond recorded history. The lake became extraordinary through persistence alone. On the evening before the first Cossack reached these shores, Baikal was already complete. On the day the first deep submersible returned from the bottom, it remained complete. Tonight, beneath layers of ice or open water, depending upon the season, the Golomyanka rises once more through dark water. The Nerpa descends on another long dive. Amphipods continue crossing the lake floor. Water circulates, sediments gather, and the ancient rift widens by another fraction. The world does not wait for discovery before becoming real. Baikal never did. It simply continues,